Hello, am I audible?
Yes, sir, you are audible.
Okay, great. All right. So yeah, so in last session we went through some of the content covered in week one, representation learning. It was a quick summary session, and we just kind of went over the entire content that was covered in week one by Arun sir. So the main plan for today's session is to explore some of the programming side of things, right? So how do we make use of say Python to better understand representation learning and unsupervised learning? So that is mainly what I want to do today. But before we go there, I maybe say for half an hour or so we can discuss questions or doubts that you may have on content. Are there any such questions?
Sir, I have one doubt in grading assignment. Like I'm not asking something you to answer, but there is one question in graded assignment,
Okay.
which according to me is like it needs some kind of an improvement. Can you just please open it?
Yeah.
So I think question number 5, near question number 5. Yeah, this question above that graph question. I think there is a graph given. Not this one. That W above question, like I think.
Yeah,
this one. So basically here they have not talked anything about the norm of this particular line L, and in the statement also, like
and no, that is by design, right? So have you studied vectors before?
Yeah.
So when I say W is this vector OR,
okay,
then that is W. There is no ambiguity there actually. There is, when I say that OR is W, W is OR, right? There is nothing more to unpack there. A vector has magnitude and direction, and it is as explicit as it can be, right? This is the vector we are talking about. This is what is W.
okay, fine.
Yeah, what is the question actually?
Actually, I can't say like ahead of the time because we are not in a situation to discuss the answer.
Okay.
But I'll ask it, like when the answer is released, I'll ask it again.
Okay.
Sir, in the same line, sir, can I ask one thing, sir?
Yeah.
So if you refer the question number 2.
Question number 2. Yeah.
Question number 2. So this expression, the projection of X on the line L. So here the O or the W is given this 1, 1, right? So it is not a unit vector. So the actual expression should be X transpose W by norm of W square, right?
I can't answer that. See, okay, let me go and just to make sure that this is not such a ambiguous thing. I just want you to. There are so many vectors. Where is the mathematics vector? I just leave you with this image, and then you can make out what it is from there. See, this is what a vector is, right? A vector from A to B is in this direction having certain magnitude, right? So here it's in this particular question, it has been very explicitly stated that O to R, OR, that is the vector. So this is along this direction OR, and it has certain magnitude as you can see from the image. right? So if W is that, then you have to make sense of these statements.
No, I'm just, that's okay, but when it is not a unit vector, then
See, that is what you have to see. The crux of the question is there. If I'm going to discuss more on that, then
okay. And sir, one more thing, just question number 5, just one thing.
yeah.
Question number 5.
Yeah.
Yeah, so find the reconstruction error. This reconstruction error is always norm square, right? Means the squared error, right?
This is you should take the squared length. That is
Squared
right.
length always.
Yeah, always squared length, right? Not the length of the error, but the square of its length.
Okay.
Okay. Yeah. Any other questions in say practice assignment or?
Yes,
Sir.
can we ask?
Yeah. Yeah.
Yeah. Last time we was discussing about some question, and you told that we can think further the next class. That's 2 question was there, and I want to come back to that question.
Okay.
So in assignment yes, there was one question related to the question number 10 or something, where the W1 should be the 0. Yes. So you explained that, and I thought about that, and I came to some conclusion.
Okay.
So here it's asking first of all that PCA. So I have one question here. So since PCA is centralized, the centralized data, and the summation of all thing is going to be 0.
Correct.
Okay, and since it is also a vector quantity, is it? So it is vector quantity, and that's why we are taking the projection of the first PCA line, no? PCA1 component.
10th question you are talking about, right?
Yes. In that question, I'm talking. So suppose a hypothetical situation where the some point is given in general, and to make the PCA, I take that projection on the first PCA line component, no? PCA1.
Okay.
So since it is the vector component, so since and also the summation of all vector is 0, that means we can say that its summation of the all individual component is also going to be 0.
Correct. Yeah.
So since it is a component is going to be 0, then it is the general W1 will become that 0. Even the W2 is going to become 0. We can say that.
Sorry, W1 becoming 0. I didn't get it.
No, it's asking here. No, what is the question? And mean center after estimating W1 in the first round. No.
Yeah.
What is the meaning of the residues? No.
Correct. Yeah.
So residues is nothing. Is the component of the perpendicular plane to that first PCA1, isn't it?
Correct. Yeah.
And which is nothing itself is the another component of that same point. For example, a 3-dimension point is there, and I have taken a component on according to some line. So there will be the another component of that particular point also, which is perpendicular to the
W1.
plane
Right.
line.
Yeah.
So since it is the vector, so its individual component is also going to become 0 itself. So in that logic, the using the vector law, we can say that W1 residue, summation of the residue is going to become 0.
Right. Yeah. That is true.
And one more logic, what I thought, that suppose it is the point is always in the space. Suppose I'm talking the 3-dimension RD, where D is equal to 3. So point is in the space, and the first PCA itself is going to arrange such a way so it's find the minimum distance. The summation should be the minimum, no? And in that condition, due to the geometry law, we can say that whenever something is going to be symmetric about some geometric way, then it is either following the maximum or the minimum. So in that case, the line is passing the first PCA1 through the point, all the points. So all the error is going to become summation is the minimum. So it is arranging in the minimum direction, the minimum way, the length. And since it is the vector quantity, it's going to summation 0. So this is the little the geometric law. So, but we can think also here that it's going to become 0.
Right, yeah.
So my question was here, in that way, I can say that W2 also is going to become 0, isn't it?
No, W2 cannot become 0, right? W2 is, I don't understand what you mean by W2 becoming 0. W2 is
like that, we take the component PCA1 and PCA2. Similarly, PCA3 also will be there.
They'll all be perpendicular to each other, but becoming 0, you mean projections becoming 0 or?
Projection will become 0 also, because that because the formula itself is the vector, like that xi minus x dot w into w, and where w is the unit vector. So itself is the vector quantity. So projection is also going to become 0.
Right. Yeah.
The way,
can you write it down, and maybe that may be a better way of. I'm not able to capture the essence of your argument. So if you can. Down.
I will try to write. Okay.
Yeah. So anyone else? We maybe.
Yes.
Yeah.
Hi Karthik, I have a query. Actually, I put it on discourse regarding that PCA thing. If you have seen, I'm still not able to get that. How do we reduce by choosing, say, the first? Say we want to reduce from R30 to R5. How do we choose the number of vectors in the covariance matrix so that it's reduced to R5? That, I mean, it may be a long explanation. So if you can put it on discourse or here.
So see, so let's take R30. You have 100 data points in R30. Okay. So that is what we have. So this will mean your data matrix is of size, say 100 cross 30. Is that right? So this part you agree, right? So there are 100 data points and these many dimensions are there. So I'll have to store 3,000 values in my computer or whatever storage location. So this is what I have to begin with. Now what we are doing is we are doing a PCA on top of X and we are reducing it to, let's say 100 cross 5, right? So now this is one way of reducing it. So you end up with just the projections on these principal components, which is 100. So the entire 100 points have now 5 components each. So this is one way of looking at the reduction. So is this what you are not able to follow, or?
No, this is basically the overall picture. How do we get the points? But how do we actually get those points? Like we are at the covariance matrix and we take out the eigenvectors. At that stage, how do we actually compute the reduced values? That is the issue, not that gross total figure like this one. Okay, I have these 500, but what are those 500? That is the issue. Like there is a projection where we project the eigenvectors on each data value. So that area I'm just a bit confusing because I'm not getting the exact figure.
Okay, right. So we'll start like this. So step 1 is you have X, which is of size 100 cross 30. Okay, so we start from there. We compute the covariance matrix, right? So that is C. C is actually equal to X into X transpose X, right? So C is X transpose X, and we have to divide by the total number of points. In this case, there are 100 points, right? 1 by n into X transpose X. So this part, till this part, is it clear? This is the covariance matrix. So yeah, this may just zoom in.
We get the eigenvalues of these and then we get the eigenvectors. That also is clear. After that,
Right. So the eigenvectors, eigenvalues, you get let's say W1 so on till W. So this will be of
30.
30.
Eigenvalues.
So this will be of dimensions 30 cross 30. So my eigenvalues and eigenvectors will be 30 in number. Right. So these are till this you are saying it's fine.
Yeah, now we take out the eigenvectors in decreasing order of eigenvalues, and then we project each eigenvector on all the 100 values, right?
Each of the 100 values you project on the 30 eigenvectors. I mean, that is a better way of putting it.
Okay.
So let's say you have xi, the ith data point. Now what you do is you project xi on w1 w30.
Say W5 because we, I think, reducing to W5.
Yeah, okay. Let's take the top. So let's have one intermediate step. Take top 5 PCs, right? So take top principal components. Assume that it is already ordered in the decreasing order of lambda. So W1 is the eigenvector with maximum eigenvalue. So get it on W1 to W5. Okay, so now this will give me how many values? This will give me 5 values, right? Xi transpose W1, Xi transpose W2. If you want to write it explicitly,
5 or 500?
5, right? This is just a dot product. So talking about these 5 values, Xi transpose.
No, each point will give 5 values, you're saying.
Yeah, each point will give me 5 values, right? So this will be what we get, right? So you are projecting a point on your new directions. You have 30 directions, but you are taking only the top 5. You are projecting each point on these 5 most important directions.
So we get 500 points total, right? For 100.
Correct. Yeah. So we get 500 points, which we form into this say X prime matrix, right? Whatever we want to call it. So let's say X prime. So that is going to be 100 cross 5.
As per the total, we should be getting total 650 points, right? Kn plus Kd.
Yeah. So this is one way of doing it where we only retain the scalar projections, right? So way of doing it.
You don't multiply with the W again, right? To get the projected matrices for getting the residuals in this case.
Yeah. So this is what we have here. We only retain the scalar projections, but what you are suggesting, which is what Sir also discusses, is the reconstruction, right? So you have to, if you want to reconstruct xi, let's call that xi. Let me call that xi(r). Okay, so this is the reconstruction of xi. Then that will be x1 transpose w1. This is the projection of x1 on the first direction times w1 plus all the way up to x1 transpose w5, right? So this is, let's say I've done it for the first point. So this is the reconstructed version of point 1.
And what about, sir, the 150 points, the representation points we need, like 30 into 5? How do we get those?
30 into 5, right? So you have, by retaining the top 5 PCs, what we have done is we have now 5 principal components. Each one is having how many? 30 dimensions, right? So that contributes 150, right? In addition to that, for point 1 we had to compute 5 dot products, right? So point 1 contributes 5 extra values which you have to save. Likewise, there are 100 points. So these 100 points, each point contributing 5 new values, that will be 500. So total of 650.
So we computed 500. How do we get the balance 150? Say?
Yeah, so these are two different So see, there are two things here. The question you have to answer is, do you want to retain the reconstructions, or do you want to just retain the scalar projections? So these are two questions that we need to answer. So if you only retain the scalar projections, then we are throwing away this reconstruction, right? So we don't need W1 to W5 finally. We only need X1 transpose W1, X1 transpose W2, so on till X1 transpose W5. Okay, so the extra 150 come from retaining these reconstructions. That is, you want to totally re-represent this point.
Correct.
Right, so then you get these 150, which is what we have discussed so far. In the next week, which is week 2, it will become clear why we also need to look at just the scalar projections, why it makes sense to only look at scalar projections. That is something which will become clear in week 2.
Okay, so right now we are skipping that 150 part.
No, we are retaining 150. Please retain this 150.
How do we get the 150 in this algorithm? Because we have only computed 500, right? Based on X into W in the point, in 0.5.
In point.
We have not computed the 150 points in this whole procedure.
Sir, is that 150 is a coefficient that we have studied in representation learning?
Yeah, so this 150 comes from storing W, right? So see, we have to understand what we want to store in your computer, right? So what are you storing? You are storing the eigenvectors or the directions, right? You are storing two things. The first thing you are storing is the direction. So how many directions are there? W1 dot 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 W5, correct? So you are storing 5 directions. So 5 directions, each dimension 30, so 150. So you have to store this. Second thing that you need to store is the projections of each point on these 5 directions. So you need to store the scalar projections. So that is what xi transpose W1, so on till xi transpose W5. This you have to do for 100 points. So for 100 points, you need to store how many values? 5 values. So 500, and therefore 650 is coming. Right. Okay. So we are always storing two things: one the directions and the scalar projections of the points on these directions.
Okay, those are just the eigenvectors, W1 to W5 of the covariance matrix, right?
Yeah, exactly.
Right, sir. Got it, sir. Thank you so much.
So for the graded assignment questions, please take into account both these things. Right? Don't just stop with the 500. So this is, as far as the graded assignment of week 1 is concerned, this is wrong. Okay, not wrong, but when we say which question I am talking about is this particular question, where we have asked what is the compression ratio. I think some question is there.
Yeah, both in practice and the graded, it's there.
Yeah, so when we say compression ratio, we are talking about this complete representation of storing where is that both the directions and the scalar projections, right? This is what we are talking about.
Yes, sir. Got it, sir. Thank you so much.
Yeah.
Sir, I have two questions.
Yeah.
One is what is the significance of the covariance matrix, and another one is the if we have a covariance matrix with us and we have a eigen vector also, so how can we compute the variance from those two things?
Okay, so what is the significance of the covariance matrix in the sense? Can you elaborate on that question?
Yeah, because we are extensively using covariance matrix. Why? What information it is giving to us?
Covariance matrix in some sense captures, see, the diagonal elements of the covariance matrix captures the variance of each of these features, and the off diagonal elements, it captures the interaction between features. So in some sense, the covariance matrix is capturing interrelationships between the features of your data set. That is why it is so prominent.
Okay, let's say we have a 2 by 2 covariance matrix. So how it is like, and we have let's say for 2 by 2 covariance matrix, let's say I think we have 4 points, right?
No, we have four dimensions or four features.
Yeah, 4 features. So how it is correlating, like which point to which point, like in that particular matrix, like x1 to x2, x1 to x3, how it is relating?
That is the covariance, right? So you have, do you know what covariance is between two random variables?
Yeah, I know.
That is what it captures, right? So the covariance matrix, if you have a C matrix, then Cij is capturing the covariance or the relationship between features xi and xj, right? So I don't know, I don't want to go into the exact formula, but it is something like this, right? So xi minus mu I and into xj minus mu j. So if you have two random variables, so xi and xj are, let's say, features I and j in your data set, and mu I is the mean of that feature and mu j is the mean of the jth feature, then this is what Cij is in some sense representing. How do they co-vary? So what is the covariance between features I and features j? So so higher value of this would mean that if xi increases, then xj also increases, something like this, right? So the relationship between features is what is captured in the covariance matrix.
Okay, and what about the variance?
Variance is captured by the diagonal elements, because diagonal elements are nothing but Cii, right? So that is the variance in the ith feature. There are d features, then the ith diagonal element will give you what is the variance in that particular feature. So it will be, instead of, you can see that the variance immediately jumps out at you if you do this, right? Expected value of x minus mu whole square is the variance. In our case, since mu is 0, the data center, it will be just e of x, expected value of x square, xi square rather. Okay, anyone else having any other question? In
I
general?
have a doubt. When we say top k principal components, do we mean the top k eigenvectors? I mean the top 5 vectors which have the highest lambda.
Yeah. Principal components and eigenvectors are interchangeable terms that we use, right? So,
okay.
So
I just wanted to clarify that. And I have one more doubt. In the graded assignment, for 1 second, question number 4, I got an answer which is not there in the option. And I think I did the procedure correctly, but I'm not sure what I did wrong.
okay. So you might have.
I got -5, -5. I got the projected vector as 7, 7, and the initial point is 2 and 5. So 2 minus 7 and 5 minus 7 gave me -5 and -2, like that.
Okay, so see, one thing you can do is you can actually draw the vectors here and see what is happening. Okay, so see, this is you can actually geometrically solve this problem in GeoGebra or say Desmos, whichever it's convenient. You kind of draw what you have, plot the vectors that you have, and see if that is the correct one. Right. So far, I don't. Others have not come up with this. So I think the correct answer should be in one of these. So
Okay, we have to do X transpose W into W, right?
that is up to you to decide, right? So see, the whole idea behind this problem, these three problems, is to go beyond formulas. See, formula is important, but you must know when to use what formula, or what is the essence of X transpose W. That is something that we want you to understand. That is what we are testing in these four problems, right?
Okay.
So when to use what, rather than see, because we are using X transpose W so often in the lectures that it kind of, we go with the formula, but we want you to deconstruct that formula piece by piece and understand what is happening. So that is the point of the four problems.
Okay. Okay, thank you.
This question number 9, could you explain the procedure? I'm unable to get how to calculate the variance.
Question number 9.
Yeah.
Uh,
I know the variance formula, but I'm not getting how to approach this.
So if you notice in the last two lectures, we have discussed this.
Yeah, variance formula you explained, mean is 0, and for centered data and variance formula also you gave. It's there in the lecture also.
Yeah, if you follow that, I think you will be able to solve it. Right, so
here, covariance matrix is given, right? So I'm unable to get eigenvectors.
you will have to make this connection, right? So there are more than this. I would be, if I give you the procedure, I will end up, revealing the answer. So
Okay.
unfortunately, I can't say more than that now.
So can I consider these two as the individual vectors, independent vectors too?
These are two different vectors, right? As given in the statement.
Okay.
Okay. Any other questions in speak's content? Since we have titled this as an open session, I just want to make sure that there are no other questions before moving on.
Excuse me, sir.
Yeah.
Sir, I have doubt in programming assignment. I don't know like how to do the questions in that, how to visit the data.
Yeah.
Can you solve any questions there?
We'll solve all of them now. We'll start solving them. Before that, I just want to finish the theory part if there are any questions.
Okay, sir.
Does anyone have any theory questions, or shall we move to programming?
So move to program.
Okay. All right. So yeah. So in this is the collab that we have shared with you all. So yeah, I hope all of you know that programming is optional, that there is one OPP which will be conducted at the end, which is again optional. You can register for that. You will get some certificate and all that is there. But I would strongly urge all of you to still take this seriously, because ultimately you won't be doing so much theory, you will be doing only programming. Whether you do a data science job or anything related to data science, it will all be programming. So finally, this is what I won't say this is the only thing which matters, but the importance that this has is cannot be overstated, right? So
then why has it been made optional?
So we have divided the machine learning courses into three parts, right? So MLF, MLT, and MLP. So we felt that machine learning techniques is already too theory heavy. So we didn't want to make the programming part graded in this term. Also based on few of the earlier runs of this machine learning techniques, we found out that both these things may be too heavy for students. So the graded programming part is totally in machine learning practices, right? So this is kind of a warm up for that in some sense. Okay, so yeah, so we are given some data set and X is that data set, right? So we look at what this X is. So first thing that we'll have to do is we'll have to load this data set. I'll come back and tell you exactly what each of these lines means, but for now we'll just execute the other steps here, right? So X is given to be some data matrix of shape n comma d, right? N is the number of samples and we have d features. So did someone solve this? Of course we have released the solution also, but in case any, yeah. So what is the answer here?
So for first code,
Yeah, first one.
sir, it is the
Zero.
x dot shape of 0.
Okay, right. So you get x dot shape, and then you take the first element of the tuple that is returned, right? So let's just go into this. X dot shape returns one tuple, okay, and the tuple is nothing but the dimensions of the array, and this array has dimensions 100 cross 784, and this is what it is, right? N cross d. So n is 100, d is 784. You want to get the number of samples, it will be the first element of the tuple. So that
That means 100 row and 784 column in
yeah,
each row.
right. 100 rows, 784 columns in each row. Okay, and by extension, this will be x dot shape of 1, right? So that is what this is. Okay, so these are two simple questions.
One question I will ask, sir.
Yeah,
You
please.
write in this same, sir, after x dot set 0, in the next line, if you write x dot ending in dimension,
Yeah, x dot ending. Okay.
here you will get 2.
Right.
Little confusion because 2 dimension means I thought ki row and this column, but again there is 100 row and 784 column.
Okay, good point. So in NumPy, right? So NumPy has this. The idea of dimension in NumPy is different from the way we use dimension in mathematics, right? So the shape, so the dimensions of a matrix, that term dimensions of a matrix corresponds to shape of an array in NumPy. Okay, so NumPy has only arrays. Okay, so NumPy has arrays, and if you have gone through this week 0 content, there are different kinds of arrays, and each array has what is called a dimension, which you just pointed out, ndim. Right? So from this conversion from mathematics to NumPy is very important. So vectors in mathematics are single dimensional NumPy arrays. Matrices in mathematics are two-dimensional NumPy arrays. Okay, is that clear? The connection between vectors and NumPy arrays, matrices.
Okay. And can you, sir, give one 3-dimensional NumPy array? How it is?
Yeah, so 3-dimensional NumPy array will be just from here we can understand. So, for example, x train is there, right? So let's take x train and also write this vectors, matrices, images. Could say an image is not a mathematical object, but still I'll just go with it. So x train is actually a 3-dimensional NumPy array. You can check the ndim for x train. It is 3. So what this is saying is that there are 60,000 images of dimension 28 cross 28. Right? So when I say x train of 0, or let's say 0 and 14 and 3, this means in the 0th image of the data set, what is the pixel value of the 13th row and second column? Do you get it? What we mean by 3-dimensional arrays? So this is x train of 0. If you just take x train of 0, that is image 0, right? Or the first image in the data set. And 14th row in that image, that will, rather the 13th row of the image. Okay, so is this 13 or?
Sir, 15th row, I think.
Yeah, you are right. So this is 4th column. Or let's say let's just use 0 indexing, right? I assume that I'm using 0 indexing so that you avoid this confusion. Yeah. So that, do you get it now? What we are dealing with here? Okay. Right. This will become clear in some time because we will be anyway plotting all this. So the main point to note is that dimension in NumPy is different from dimension in mathematics. Okay, so right. Yeah, so that is x dot shape of 1. So now we come to this part. So each row is an image, right? Each row is an image, and we need to visualize this image. So the library that we use to visualize images is matplotlib. So one way to do that is that first import the library. PLT is the tool, or pyplot is actually one of the modules in the matplotlib library, and you are importing that as PLT. PLT is an alias, right? You could say import matplotlib.pyplot and just stick with that, but every time we have to keep calling it matplotlib.pyplot, right? So instead of doing that, we are just having a short or nickname for this, right? And this nickname is PLT. Okay, so visualize one of these images. So let's take, say, the third image in the matrix. Okay, let's first look at what is the shape of that particular image. So that image is what? A 784 dimensional vector. All right, so this image is a 784 dimensional vector, and in order to plot an image, you need it to be in 2 dimensions, right? Here I'm talking about the math dimensions, so it should be of size 28 cross 28. Right. So what we do is NumPy has a facility to reshape an array. So when I say x of 3 dot reshape, I will get something like this, and just to verify that we have the correct shape, we just run this again. Image dot shape is 28 cross 28. Clear so far what we are doing?
Yes.
Yeah.
Please explain this once again.
Okay, which part is unclear? This reshape or?
No, so when you are reshaping, you are giving 28 into 28 because to plot an image, I need CS.
You need shaping, yeah.
Now, in case this 784 is not a multiplier of some square value, then
you can still plot, but it will be a rectangular matrix. Okay, so first let me quickly tell you what this, in case some of you are not clear about what reshape does. Let me take a simpler example. Okay, so you have a matrix, you have an array here, right? This is a NumPy array, and It's a one-dimensional array. So 1, 2, 3, 4, 5, 6. Think about this as 6 features, right? So now what happens when I reshape this as a 3 cross 2 entity? This is what happens, right? So 1, 2 goes on the first row, 3, 4 on the second row, 5, 6 on the third row. So there are 3 rows, 2 columns. Okay, this is what reshape operation does. We could also reshape it as 2, 3. Right? And then in that case, it will be 2 rows and 3 columns. Okay,
But these two will represent two different image, right?
They will represent 2 different images. Yeah.
Sir, how do we decide? See, 28 cross 28 is a 784 is a perfect square for 28 cross 28. So we know that RGB values is stored as in a black and white image is being stored as 784 feature matrix sort of thing. So how do we decide we have to take those 28 in that? I mean, how do we know how to place those 28 by 28 images?
Whether you have to rotate it or just
like the values can be, it can become a totally different image, right? If we don't place the values correctly.
Yeah, you are right. So that's a good point. So what happens is, what I have done, if you notice, is the data is coming to me as an image only, and I am reshaping the data in a certain way. So for example, let's say, so I need to tell you how the data has been constructed. So the data was given to me like this. Let's say this is a 3 cross 3 image. Okay, so someone gave me this as the data, and what I did for us to do machine learning, we need to represent this at least in the week 1 as features, right? A single feature vector. So what I did was I reshaped this to one single vector of length 9, and I gave this to you as the data set. Okay, so what you have to do now is you have to reshape it back. And the nice thing is that when you are reshaping it back, it follows the same method that was used earlier, right? So this is some kind of row first form, right? You take 1, 2, 3, and then you take the row and put it next to the first row. You don't do it column wise.
So right? If this was rectangular, say you were doing 1, 2, 3, 4, 5, 6, and you want to reshape it back, and you did x dot reshape 6. Then again it will come back to a row shape form, like you said. It will be row first, and then it will be 1, 2, 3, 4, 5, 6. That's how it reshapes.
That's how it will be, but we can't reshape it to 6, right? Because the total number of elements should be consistent. You have 9 elements, then if you reshape it, the number of individual values should be retained.
Yeah, I meant if it was a 6, if it was 1, 2, 3, 4, 5, 6.
Right. Yeah, then that will be retained. Yeah. Okay, so I hope reshape what is happening is clear to you all. So what we have done is we have reshaped this 784 dimensional vector into one image. Okay, if it is not clear, let me know. Now we have to plot this image. Okay, so T is out of bounds for axis 0. Okay, so what happens is I have used this x, right? So I have to restart and run also. I hope you're all aware of this problem in NumPy. See, now if you see what the shape of x is, x is now of shape 3 cross 3, right? Because I have in my one of the cells I have made x to be this, right? So the shape of x has now changed. And did you all get what the error was and what I did?
You have changed the value of x.
Yeah, so I changed the value of x, and even though this cell is above the later cell, this x value is changed, right? So in such cases, what you have to do is you have to restart the whole runtime, or you have to restart NumPy. The way we do that is runtime, restart runtime, So it will ask you if you want to restart the runtime, all the local variables will be lost. It's okay. So this is just to make sure that the old value of x is forgotten. Okay, so I'm running this again. I'm running this also. Okay, now we have x as it is. Okay, so this is how that particular image looks. This is an image of a 2. Now, if you don't want this color business, you could use a different map, right? You could use a grayscale map, in which case this is how the actual image looks like, right? So that coloring is something that NumPy does. This is how the actual image looks like. Okay, any questions so far till this stage?
Yes, sir. This picture has whatever is showing here. So that's I was talking that we can manipulate the pixel also, which is looking the fade gray or fade white.
Right. Yeah.
And after manipulating, making that fade gray in the completely white, is that memory of that picture is going to change or not?
Memory will not change, right? You're only changing the intensity of, you're only changing the values of few pixels, right? So for example, let's say I want to make this first 5x5 cell, I want to make it white, right? So I will do something like this, right? Let's say I do something like this. So what I've ended up doing is I have made this part white, right?
Right.
But my memory doesn't change. I still have only those 784 elements to work with.
Okay, I have written the code for that. Where is the 2 is written? So I change instead of making the square the white color, I change that entire 2, whatever the written. So I change that even the gray color in the white. So it's completely look. There is no hazy border of the 2. It's looking the completely 2. So we can play with that pixel manually with coding.
Right, yeah. But in that process, you don't change the memory. You only change the appearance of the image.
Okay.
Right?
Yes.
Okay. So, yeah.
Sir, what was the 255? Sorry. Earlier image, 255 was mentioned. What was that?
So these are pixel values, right? So each pixel, if you look at each pixel, it can take values between 0 and 255. So it's some 255 is what? 2 power 6, 2 power 8 minus 1 or something, right? So whatever bit byte, 8 bytes or whatever, right? So 8 bytes can represent how many values? 0 to 255. So that is why we use 255. So 255 means white, 0 means black.
Okay.
Excuse me, sir.
Yeah.
So could you please explain the very first code, that the main code which was initially given?
We'll come back to this. I will come back to this once we have little more context. This requires few more things that we need to understand.
Okay.
Okay. If you want a very quickly, I'll tell you what we are doing is we are getting hold of all images which have label 2, which are images of 2, and we are taking the first 100 of these images and we are reshaping them into feature vectors of size 784. So we are doing 3 things here. We are taking all images of data points which have label 2. There are many such data points. We don't want all of them. We want only 100 of them. And then we are converting them into feature vectors of size 784.
So sir, here, what are the images that we are getting? Images of numbers, right?
Numbers, yeah.
And so what is the meaning of X train or Y train? Are these related with some train, or is this something like that?
No, so these are like training and test data, right? So this is from a supervised learning setup, which we'll study in week 5 onwards. So you divide your data set into training and test parts, right? So did we do this in MLF? I don't know. So, but X-train is just one subset of the data set. That is what you need to remember here.
So these codes and these things are very new to us. So I was facing some problem in understanding these things which you are explaining right now. So I thought this must be related with some this code which is given very first. So I thought it should be explained. So if you're going to explain it later on, then it's okay, fine.
Yeah. So in fact, you don't need to understand. I mean, it's good to understand, but you are not required to understand this for solving the other problem, because this is just ideally you should have hidden this, but in Colab there is no feature to hide this from. You can hide it, but you can still reopen it. Anyone can open it and see what is there. Right. So this is some kind of hidden code. Treat it that way for now.
Okay, sir. Thank you.
Yeah. So now we move on to the.
Sorry, sir. Hurry up.
Yeah.
If you scroll back up, the dot reshape further up. The dot reshape -1. That is the axis to make it into a column vector.
So why we are reshape? There are certain number of points. Let's say when you do this, there are 100 points, right? Now 100 images, each of size 28 cross 28. Ideally, we want to reshape it in this way. So this is how it should be. But sometimes what happens is you may not know exactly what the first dimension is. So in such cases, NumPy has a facility which allows it to compute this first dimension on its own. Right. So for example, if I say I have a matrix A of size. Okay, so now let's say I want to reshape it as this is 2y3, right? So there are totally 6 elements. Now I want my last dimension to be 2. Okay, this is how I want to reshape it. Now let's say for whatever reason I don't know that the first dimension has to be 3. So if I do -1, what will happen is that NumPy will figure out that this has to be -1 on its own. That is the use of this -1. Right. So I could explicitly write 3, 2. But let's say for whatever reason I don't know that this has to be 3, then I can write -1, 2, and it will still work. All right. I hope that answers.
Yes, thank you.
Yeah.
Excuse me, sir.
Yeah.
So like in NumPy, we have so many methods and like attribute, right? I mean, what is the like how we can distinguish between these methods and attributes? Like, how do you know that this method should be used in this case? Like,
how do I know which method to use when is by practice only, right? So that you develop by practice. Okay, there is no.
Yeah, also in here you have used that shape, right? X dot shape.
Yeah.
So this is the attribute, right? This shape that you have used.
Shape is an attribute, yeah.
Yeah, and the reshape is the method.
Reshape is a method, yeah. It comes with practice, right? Which to so for example, there are some methods in NumPy. For example, if I want to find out the sum of this matrix, I could either use NumPy.sum of A, which is a NumPy method, meaning NP dot. So it's a method of the NP module, or I could also do A.sum of. Both will give you the same answer. Right? This is a method of.
One is the method of the NumPy array.
Yeah, second one is the method of the NumPy array. Okay,
So
so
why are we getting the same arrangement when we are replacing 3 by -1?
because it is 3, right? So when we do this, this 1 here stands for 3 because -1 numpy is going to do. There are 6 elements in A, so let me do 6 by 2. That is what the -1 stands for. So you will get the same array if you do a dot reshape of 3 comma 2.
So how will know that in negative which value stands for the corresponding positive value?
No. So you have to treat this as a special value, right? -1 means compute that missing dimension for me. That is what. So it's like you are sending numpy a message saying, I don't know what this dimension is supposed to be. I don't want to bother computing it. You compute it for me. That is what -1 stands for, right? So
Okay. I got it. Thank you.
yeah. Okay, so now we have to center the data set, and how do we center it?
Subtract the mean. We subtract the mean from the.
Yeah, right. So we subtract the mean. So there is again very simple method for finding the mean of a data set. X dot mean will give you the mean, but we have to be careful along which axis we do this. Since we have x's of shape n cross d, right? So we want to do it along that axis where we have all the samples. So you have to compute the mean along the axis 0. Okay, so this can be a bit confusing if you are seeing it for the first time. Is this part clear to all of you what I have done here?
Sir, here we are finding mean across column. No.
We basically centered the whole.
That n.
So x is equal to 0 is a mean across column.
Okay, so see, I always understand it this way. The row column kind of I get confused often. So what I do is, for me, let us add few more here. 4, 5, 6, 7, 8, 9. Okay, so this is A. Now
There should be brackets.
Yeah.
Oh, right. Okay, so 1, 2, 3, 4, 5, 6, all this, right? This is a 5 cross 3 matrix, right? So now let's look at what this does. What kind of okay? So this is what this is doing is this is adding all the rows, okay, and dividing by 5. So what this is doing is it is doing a of 0 plus a of 1 plus a of 2 through this explicit computation. There are only these, right? So this divided by 5. I'll print both these and then we'll see what. Okay, so this is what x is equal to 0 means. So the way I understand it is you do it from top to bottom. Right, x is equal to 0 is top to bottom. You kind of sit on top of the numpy array and compress it. Right, you add it.
For particular column, it is summing over all the rows for a particular column.
Correct. Yeah. It's summing all the rows, right? Okay, top to bottom. Okay. And let us also look at the other one. A dot mean of x is equal to 1 is this is
for particular row, it will be sum over all the columns.
Right. Yeah. So the way I understand it is we move from left to right. So explicitly what this is doing is take the first entire column. Okay, so there are 3 columns. Okay, you do this and you divide by 3 because there are 3 columns. So that is what these two axes mean. Okay, is this part clear what we are doing?
Yeah, right.
Yes. Okay. So once that is clear, we can, what we need here is each row is a data point for us. Each row is an image, right? So we need the mean of these images. So we add all these rows from top to bottom. So that is why we choose axis equal to 0. Okay, so that's what we have done. Extra axis 0. Yeah.
Sir, in the case of sum, sir, there is a mean. In the case of sum, how axes work?
Same way, right? Whatever way I just showed, it will work in the same way.
Okay. Sir.
So the axis is a common principle. So yeah, so once we have centered, I hope you all got what centering means. You can now verify that you have centered it correctly by finding the mean of the mean centered data, right? If you run this, you will see that they're all actually zeros, but because of numerical precision, you will see that this is 10 power minus 15. Essentially, these are small values, right? So you can, just to be sure, you can sum this and see what you get. You get a very small value, right, which is nearly 0. Okay, so just to verify that you have done it correctly.
Because without getting the mean, also the sum will give the 0 only. No?
Yeah, without, yeah, your without.
Because that mean is nothing, the sum by the sum number. So sum is 0, by mean is also 0.
Yeah, true. Right, so this is the mean centered data. Now we come to the covariance matrix part. So covariance matrix is what? Once you have the mean centered data. So let's quickly see what is the shape of this. This is still the same shape. So what we want is x prime dot transpose. This is x transpose x divided by the total number of examples, right? So total number of examples is 700, right? 100 examples. So that is the covariance matrix. Is this part clear, or do you have any questions? X transpose x by 100.
Sir, I calculate this covariance matrix, but to cross check whether my matrix is correct or not, I enter through this formula, but it is not coming. The answer is not coming.
Sorry, which did you come? What did you come to?
So I compute this formula 1 by d square root under to check whether my covariance matrix is coming right or wrong.
Okay.
But the answer is not matching, sir.
With the portal answer, is it?
Yes.
Okay, so let me just see what the answer should be. So c square, and if you sum this, and if you take the square root, and if you divide by d square, which is what we are supposed to do, I am getting the value of 1.36. What is the answer actually?
Yeah, answer is 1.36, but I got 136 point something.
Sorry, you got what?
136.48.
136.48. I think you haven't divided by d square, because it's like you have divided by d, something like that should have happened. D is 100, right? Basically. Oh no, sorry, D is 780. N is 100. So did you miss n into D here?
this value is matching. Problem number 4 is correct. I'm getting 0.23.
I think you have to divide by C dot shape of 1.
C is like both are 784, right? So C dot shape is like the same for.
Yeah, it's a covariance matrix. Yeah, fine.
Okay, so can you paste the code here in the chat, whatever code you have for that cell?
Okay, sir, I am testing.
So are the others following what is happening? Do you have any questions or?
Sir, can you just explain this axis part once more? Confused.
Sorry, I am not able to hear properly.
For problem 4,
Problem 4.
this axis part you just explained, but I'm confused still. What?
Axis part. So, okay, so you have this. Which part is not clear? That this first top to bottom thing, or
No, top to bottom thing I understood. Like left to right, how it is. This left to right part, it works so much.
left to right is what we are doing is we are. So we are adding the following things, right? So we are adding 1, 4, 7, 10, 13. Right, this is one vector, right? We are adding this column with 2, 5, whatever, 2, 5, 8, 11, 14. We are adding this vector with this vector, and we are also adding this third vector, which is 3, 6, 9, 12, and 15. Right, so left to right is these 3 columns we are summing together and dividing by 3. That is what we mean when we say A dot mean axis equal to 1.
Okay, and for top to bottom, we are adding this all row wise and then dividing by 5.
Yeah, exactly. Yeah. Okay. Chat. I got the chat. Yeah. Okay, so this is explain. So what is your explain here? Explain is.
Explain, sir, what you have calculated in above, sir. For the problem number 4.
Okay, so see, this should not be x into x transpose, right? It should be x transpose into x, no?
Sir,
what is the?
I checked in both ways, sir, because there is one confusion because NumPy is always stored everything in row wise.
Yeah, but see, if you notice this, that two are different, right? Xprime is, that is Xprime. Xprime is of shape 100 cross 784, right? So if you do Xprime into Xprime transpose, right, and if I take the shape of that, that will be 100 cross 100, which is not that covariance matrix, right? Our covariance.
Why are you taking at the rate of?
That is matrix multiplication.
Okay, got it.
Okay, so we are multiplying the two matrices. So to get the covariance matrix, remember that n cross d is one shape, and then we should multiply this with you are multiplying this with d cross n, right? So you end up with n cross n. Ideally, what we should do is we should do d cross n times n cross d, right?
Okay.
So I think it should be, this is the problem, right? It should be X prime transpose X prime. Then you will get 784 cross 784.
Sir, okay, sir, you go ahead. I just cross check.
Yeah. Okay, so that is the centering. Now compute the first and second principal components, which is what we have to do. So we have the matrix C, right? So C is of shape 784 cross 784. We need to compute the eigenvectors of C. Thankfully, NumPy does it for us very easily. So it has a routine called eigen h, right? Eigen h. So what eigen h will do is, so if your matrix is so forget about, if you have not done MLF, forget about what Hermitian means. If your matrix is a symmetric matrix, then it will return the eigenvalues and eigenvectors of the matrix. Okay, so let us just do that. So this is what it will do. Now the nice thing about this is that I'll just print the first 10 eigenvalues. It gives you the eigenvalues in ascending order, right? So let me take the last 10 so that it becomes clear. So notice that these are all in ascending order, right? So that is what is the power of this eigen h. It will compute the eigenvectors and eigenvalues, and the eigenvalues will be sorted in ascending order. So what we need is the first and second principal component. So we need to take the last eigenvector, okay, and the last but one eigenvector. These will be W1 and W2. So is this clear, or so this may not be clear to some of you. If it is not clear, please let me know and we can discuss this part.
So also in this like eigen vector, the eigenvectors are stored in column wise, right? Not row wise.
Yeah, these are stored column wise.
Sir, notation is not much clear, like eigenvector or colon, then -1. We can't do only -1, so we can get last one only.
So if we do -1, that will give you the last row, but we want the last column, right? So that is why we do colon. Colon meaning take the entire column, or rather take the entire all the rows in that particular column. So let me take this simpler example of, let's say, every time I'm doing this, so something simpler now. So let's take this matrix A. Okay, now A of 0, I'll print out so that now A is this matrix. A of 0 is what? The first row. On the other hand, A of colon comma 0 is the first column, 0, 3, 6, 9, 12.
Oh yeah, okay, got it. Yeah.
Okay, so that is what we are doing. We are doing A of colon -1, which is the last column, which is 2, 5, 8, 11, 14.
Yeah.
So
colon means for every row -1 last column, like that.
Yeah. Colon stands for just include all the rows. Okay, so that is this clear to everyone what we have done, W1 and W2?
So if we
can you
doing
plot this?
-1 comma colon, then sir, for every like -1 comma colon, what will be, sir?
It will be the last row of the matrix.
Yeah. Sum over all the columns. No, not sum. For last row for all columns.
Yeah. Yeah. So any other questions with the W1, W2?
Sir, can you, sir, also paste plot the first two?
Yeah, that we'll do next. But before that, any questions in how they are computed?
Excuse me, sir.
Yeah.
Sir, the format in which we get the eigenvalues, are the eigenvectors arranged column-wise?
Yeah.
All right, sir. Understood.
Yeah. So I think just check that one. So this, if you look at the returns two objects, 1D array containing eigenvalues and a 2D square array or matrix of the corresponding eigenvectors in the columns, right? So in columns.
All right, sir. Thank you, sir.
So could you print the W1, W2 values?
Values of W1, is it? It'll be like some 784 dimensional vector. Right? So when we plot it, it will become clear. So W1, I'm going to plot the image corresponding to W1. So I just like what we did earlier, we are reshaping it to an image, and then we are doing plt.im show of with gray color, grayscale, right? So let's do grayscale. So this is the first principal component that we end up with.
Sir, why does it look like a number? I mean, it is a direction, right? It is like a component, a principal component. Why does it look like a number? I mean,
so the principal components capture the essence or the most important directions in the data, right?
Yeah.
And if you notice what we were discussing earlier, the data is made up of images of the number 2.
Yes.
Okay, so what it tries to do is it captures the most important template that represents the image 2 of all the images of 2, all the 100 images of 2 that we have. Roughly, this is how the most important features of an image looks like. Right, so that's why it looks like a 2. So there are different ways of writing it, and so maybe we can, if we choose different images, we'll get to know that. Right? So this 2 is like this. Say the 40th image is or 34th image is slightly different, right? So all these variations are there in the data, and your principal component is capturing some template or some representative direction. So it is bound to be a mixture of all 2s, right? So this is one kind of 2. So it's not average. Average is the wrong term for it, but the most significant features of a 2 is captured by W1. Okay, so we could do this for W2 also. This looks slightly less useful, right? And yet we can still kind of make out a 2 somewhere out there, but not that much. But yeah,
it's like W1 will store the most of the features for the, right? Like that.
Not exactly, but
I mean, it is the most like the top most the principal component. So that's why like the two was kind of clear in the first like W1.
Yeah, true. Okay, so yeah, so now we have to find the smallest k for which the top k components capture 95% of the variance. So the eigenvalues contain the variance, right? So each eigenvalue gives you the variance in that particular direction. So what we are going to do is we are going to get hold of the list of all eigenvalues. What I'm doing is I'm reversing the list, and the reason will become clear. The first, say, 5 eigenvalues should be the top eigenvalues, right? So now it's sorted in descending order of eigenvalues. So This is the total variance in the data set along the 784 directions. Now, what I need to do is these are the first k directions, right? The variance in the first k directions. Now, I need to go from 1 to, let's say, 784. Or I can just say a length of values, right? So if I do this, I get hold of I made a mistake somewhere. Why is it saying 1? Okay, so it's let me just print the first few. Okay, right. So do you see what is happening here? The first eigenvalue or the first direction alone is capturing 18% of the variance. If you add the first two directions, then you have 27% of the variance. And let me add a few more. If you add 50 directions, you get nearly 94% of the variance, right? So answer I think is 52. So let's just so somewhere around 52 directions you cross the 95% mark.
So why reversed here?
I'm sorry?
Why reversed?
Reversed. Okay. So the eigenvalues that you get right from this function, they are all sorted in ascending order. So I want the most important eigenvalue, so I need to look from the back of this list. So that's why instead of doing that, I am reversing the list so that they are sorted in descending order.
Okay. The sequence has changed into reversed order.
Yeah.
Okay, got it. Thank you.
Okay, so did you all get what is happening?
Can you just explain this ratio statement once again?
For this one.
Ratios. So what we are doing is so this is what I'm doing. Let's say I take the first three principal components and the variance along these principal components. Okay, so this is the variance captured by this first three, right? I am dividing this by the total variance that is present, which is the sum of all the eigenvalues. Okay, so what is this? This is 0.34. This is what I am computing as my third element in the list. So this is the third element of ratios. So fourth element of ratios will be one more component I'll add. Right, so that is what ratio stands for.
Oh, okay.
I think it should be 3.
This will be 3. All right, so I hope it's clear what ratio stands for, and then it's a simple piece of code for seeing for say k in ratios. If it becomes greater than 0.95, then you just break out of the loop, and the value of k that you have is the okay. What happened? So this is not for k comma ratio in. So you just go through a particular ratio, right? So when does for 52, for the 52nd principal component, it becomes the variance exceeds 95%, right? For the first 52. Is it the first 52 or 53?
Sir, I think it will be
3 I am getting.
equal to the if statement. It will be the greater than equal to 0.95.
Yeah, so that is correct. But in this case,
K is coming because 52 because when 53 is happening, it is breaking before that.
in 53.
I think the indexing start from 0, so that's why I guess.
Yeah.
0 it's starting from, yeah. So it will be from I have to take from 1. K plus 1 to print.
Okay, so now the answer is, what is the smallest value of K? Is it 52 or 53?
53 is that answer.
Okay, so if I do,
Sir, but indexing is starting from 1. It's written in that third line.
third line, right, starting from 1. So let's do 52. So if I do 52, then I am taking how many? I am taking, there are actually 52 values in this list, right? 0 to 51. So if I divide this by, I'm getting 0.94. Okay, so it's actually 53 then. The answer should be 53. I think I have to change it in the portal. Is that right? 53 should be the answer, right?
Sir, it is in the 53 only in the portal, I guess.
Oh, in the portal it's 53, is it?
Yeah,
Okay.
yes, sir. 53 only.
Okay, right. So answer should be K plus 1 according to our computation.
Sir, is it necessary to means if I have a value of 94 point something, I have to cross this 95?
Yeah, that is the heuristic, right? I mean, if you stick to that rule, then you have to be, you need to respect that rule basically.
Because I just have one, in this particular case, I just have one query. One of the assignment question for solving this K value, when I am getting 94 point something percentage with the value, say K value is X. But when I'm adding one more eigenvalue, this 94 is jumped to 98%.
That is fine. That is fine. Still, you have to choose that value.
Oh, I have to cross this 95.
Yeah, this 95 you have to cross. Right? Even though you may be at 94.99, right? But still,
but
you have to cross 95.
Sir, if I think in this way, because like sir, you have only compute W1 and W2 and gets an image of 2. Okay, most of the information. When you are adding this W1 and W2, you get a better image than W1 and W2 because some more information get added. Okay, like that you are adding. See, when the data set is very huge, so what is the meaning of then compression? I am adding say 94.8 and 95. It's hardly I am adding any information, but to do that, I am basically adding one more principal component axis, which may incur so many data points.
You are right, but 52 or 53 out of 784, right? Which is not such a bad thing. See, 52, we are choosing 52 out of what? 784 directions, right? Now, instead of that, we are doing 53, which is like 66% to 67% of the principal component, which is okay, right? So it doesn't, it's not going to, I mean, not even 67, it's 6.7 to 6 point something. What percentage of the principal components are you using? Top 53 or top 52? There it's not too much of a difference, right?
The cutoff line is I have to cross this 95% of that page.
Yeah, but it is not a hard cutoff line. See, the cutoff line we have is a heuristic, right? This at the end of the day, it's only a heuristic. It's not like a,
because here you are calculating 53 or 52 out of 784. So you are saying this, but the assignment question we have only 4 or 5 eigenvalue. If I take 3, then it is 94. And if I take 4, it is 98. Then 3 by 5 and 4 by 5 will have some.
Correct. Yeah, there it makes a difference, but you have to cross the 95, or at least it should be equal to 95.
Okay.
Okay, so we now move to the last problem, which is actually reconstructing the. So this is the test image, right? So let's quickly visualize what the original image looks like. I'm doing this again grayscale part. So this is how it looks, but what we have to keep in mind is that whenever we do PCA, we have so far mean centered the data. So we are supposed to center this data set, right? Sorry, we have to center this image. And that is what we'll do first. Okay, and then we'll visualize what this mean centered image actually looks like. Okay, so this is what we need to now reconstruct. Is this mean subtraction part clear?
Yes, sir.
Okay, let me call this mean test image just so that okay, so now here I'm going to write kind of a slightly complicated code. So bear with me for that. See, you can find out these different values of k's, right? So I'm not going to do that part. Let's only take assume that you have some value of k, right? And you want to take the dot product of the image or reconstruct this image by using the top k principal components, right? So you essentially want to do this. Mean test image dot product with the eigen vector -1, right? -1 is the top principal component. So this is what? This is X transpose W. That's what this means. Into W1. Okay, this is X transpose W1 into W1. I want to do this for, say, the top 20 principal components. So what am I going to do? I'm just going to do -1 -i. Here I'm going from back. Okay, so what I'm adding this to? I'm adding this to what I call a reconstructed image, right? So this will be a set of zeros, right? 784 zero values, and I'm going to add the reconstructions one by one to this array. And finally, I can see what this reconstruction is by reshaping it to 28 cross 28. Okay, so that is kind of a lot of things, which is why we didn't get the correct value.
Sir, eigenvector, there should be a column, I guess.
Oh, right. Eigenvector -1. Okay, so I hope you see now what is happening. This is what we wanted to reconstruct. We are kind of there, but it's messy because we have taken only the top few principal components. Let's take even less and see what happens. surprisingly it's kind of better. So this is probably not the best example of PCA. Arun sir has done a better example using what is called eigenfaces, the face data set, which you will see in the first video of week 2. Right, so that's probably going to give you a much better grasp of what PCA is. Right, but basically this is how you do the reconstruction. You take the dot product of the mean test image on each of the principal components, and then this is the scalar projection, right? X transpose W into W you have to do. Now, since this is unit vector, I don't need to divide by norm W square, norm W and all that, right? So this X transpose W into W is correct here. Okay, any questions about this reconstruction part?
Sir, we are taking the top k lambda values because the value with the highest lambda gives the most variance, right?
Right. The value with the highest lambda corresponds to the principal
PCA
component.
with most variance.
Most variance, yeah. That's the variance view. Yeah, you are right.
So we are taking the mean, right? The code above you were taking until 700 and yeah, in the code above, yeah, problem 8. So we are taking the mean from like first 2 and then first 3, first 4, and seeing when we reach a 95%.
Yeah, yeah.
Okay, okay.
Yeah. So we reach 95% of the variance, of the overall variance, the moment we hit 53 principal components.
But
right?
that's just the mean of this eigen values, right? How is that? Okay, that is translating to variance.
Yeah, so the eigenvalues are nothing but the variance, right, in a particular direction. So lambda 1 is the variance of your data set in direction.
Okay, okay, got it.
Right, so that is why your eigenvalues are so important, because they represent the variance along the principal components.
But sir, this is eigenvalue is the variance. This is only true when the data is centered.
Correct. Only when the data is centered.
So, what kind of image, sir, if I plot this all the 95%, that means 53 in the last for loop?
It doesn't look very good. I can say that much. It looks bad. Right, so I'm kind of still a bit unsure of this. I have done it here, but I'm kind of still unsure. So what you can do, some experiments that you can do is you can do a lot of changes here. Like, for example, you can take all the 5 images, right? You can restart the runtime and run everything. So this will give you a different set of data set to work with. Okay, so this is how it look like for. So this is the first, second principal component. If you choose 5 as the number, and test image, I didn't change. It's still 2, right? So that's why it didn't work. You could choose. You could do a few more things, right? So what happens if you choose more number of images? Let's say you choose 1,000 images. I don't know if 1,000. Yeah, I think 1,000 images will be available. So how will that change the problem? This is like effect of the data set size on the principal components. These are some experiments that you can try. So these are, and so you see 2 lines here, right? One which is slanting here, and one which is like vertical. Apparently, these are like most important things. So look at our test image. Test image is like some very weird name. And this is the reconstruction that we get. One another experiment that you could do is you could just throw in the entire data set without choosing any particular label, but this won't give you such a say let's choose 10,000 images, and so we are now working with 10,000 images, but not of a particular digit. It's like all digits thrown into it. So 10,000 cross 784. If you look at the principal components here, see it's a total kind of upma mixture kind of thing. There is nothing interesting that we can make out. So there are zeros, there is some one in between, right? So yeah, so that's all we had for today. Any questions?
Sir, so the gist of this is that we were able to express the test image, like we were able to visualize the test image properly with 53 principal components. So it is like storing lesser data.
Exactly, that is the hope. See, I don't know if we were able to convincingly show that in the collab, but that is the idea. What you said is the idea. Okay. We are able to use fewer number of directions and represent some image.
Okay.
Now, sir, if I use all 784, then I should get exact what I have in the test image. The same I can reconstruct, right?
Yeah, ideally you should see that is you are correct, but for some reason I don't know what mistake I am making. I am not able to get that. Okay, here it's coming, but somehow for the earlier thing it was not turning out so neatly. Yeah, but if you use all 784, since the 784 directions form a basis for the space, you will get the exact image back.
And
earlier you were also using 100 test images, training images. Now using 10,000. That increases the.
Right. That should also, I think, make a difference.
Yes, sir. Can we calculate the reconstruction error?
Yes, you can do that also, right? So reconstruction error should be recon minus mean test image, right? Mean test image. So this square, and then you sum this, and then you take the square root, right? So this is the L2 error, L2 norm. So it's very small, as you can see. I think, yeah, that's a good point. We can maybe do that. That will be more revealing. Yeah, so nice. Yeah, that's a good point. Yeah, if you use only 53 components, then much higher.
Then this will be increased. Yes, from here we can actually able to differentiate what is this.
Yeah. So what is the value of 95% that we have? 150. So for this, it's 150. So if we do 150, how much? How do we? Let's see how it looks. Yeah, 150 is decent, right? I think, yeah, then 150 is decent. And if you use for 150, what is the reconstruction error? It's around 525. Maybe if you use, say, 300, might be even better. 367, yeah. So that's a good point to close the thing, right? So you have, if you can compute the distance between the reconstruction. So this is not the reconstruction error that you have to do in a graded assignment because the square root is not there. So there it should be length square. Anyway, any other questions that you have? If not, we can close.
So can we have those that face eigenface data so that we can try to write the program and check?
Eigenfaces, huh? I don't think the code is available to us, but you can download that. See, the whole data, the procedure is the same. You just need to change the data set. So think this is publicly available. You look at yeah, so this thing is publicly available. So if you just copy this, download these images and run PCA on it, you will be able to get it.
Okay. Okay, sir.
Okay.
Sir, just a quick question. Can I ask?
Yeah.
Yeah. So, for any numpy array, say x, sum of bracket under x and x dot sum gives different answer. X dot sum gives, no, I think sum of x gives like a array, no, a vector, and x dot sum gives the one value, addition of all.
It should
like sir, do just x dot sum and sum x. Yeah.
should be the same,
And
right?
sum. Oh, np dot sum. I was writing only sum and bracket under bracket
Okay.
x.
Okay. So sum of x will be a Python sum, right? It'll get
Yeah.
so it's a.
But sir, x is a numpy array only, no? So.
Yeah, but sum is a Python built-in function, right? It's not a.
Okay. np dot sum. Okay.
Yeah.
Okay, sir. Thank you.
Okay. Any other questions? If not, we'll formally close the session. Okay. Thanks for joining. I think that's all we have for today.
Yeah. Thank you, sir.
Thank you,
Bye.
sir. Thank you.
Thank you, sir. That's quite helpful.
Thank you, sir.